Okay, so let's look at this question. So this question is basically on the best fit, right? So we have given this curve. So what, let me read it out. The problem finds the curve which gives the best least square fit to the points this. So these are the points, right? So in first part what we have to write is the three equation that is in the matrix form. So these points will satisfy this curve, right? So this t value is here, and so when you will put this value you will get the set of linear equation, and after getting the set of linear equation you can form, or you can write the set of linear equation into more compact form that we can call as a matrix equation. That is what we have to write at the first part. Now in the second part we have to look for the solution. Let me first of all write down the first part, right? So we, after putting this value to this equation, what we will get is c plus d is equal to b, sorry, 6, and c plus 2d is equal to 4, and c plus 4d is equal to 0, right? So these are the set of linear equation. We can write this linear equation in matrix equation like this: 1 1 1 1 2 4, and c d is equal to 6 4 0, right? So this is nothing but a, you can say it as x, and this is b. So we have written down our set of linear equation into the matrix form, right? So this answers your first question. Now second question, what we have been asked, that find the best x hat, right? So this is x, right? Here this is x. So but we have been asked that x hat. Okay, let me just ask you one thing, that if this b is in the column space of this a, we will have the solution, right? And we will find the exact value of this x that will exactly satisfy this ax is equals to b. But if this b is not in the column space of this a, then in this case we look for the x hat. That means we look for not exactly b, but we look for b that has been that we look for the part of b that has been projected into the column space of a. And why we are looking the projected part? Because that projected part will give you the least amount of error. So that is why we are looking for not the solution for the b exactly, but the part which has been projected into the column space of a, that we are looking, right? And that, why particularly that projected, why not other part of the b? Because that particular projection will lead you to give the best fit, I mean to say that you will get the least error in that case, right? So now let's solve this b. So now we will be solving. So this b, so now what we will be looking, that that there would be some space in a, or you can say let's suppose that, so there would be some space in a that would be the projection of this b, right? And yes, and this will be perpendicular or orthonormal to the vector e, so that will give you 0. So this vector, so let me just give you an analogous picture as per the line projection. So this is the line, right? And this is the vector b, right? This is the vector b, and what we do is we project. Let's suppose that this is a line, and we are projecting this b to this line, and let's suppose that this on this line a vector a is there, right? So after projecting, what you will get is the some amount of a or some scale factor of a, that this length, right? And this will be the this will be the other component of b, that we are calling it e, right? Now you think at this line as a subspace, so you can think at is a matrix a, and this is some amount, some combination that we are taking. So that is what I have written. So I have taken the projection of b that will fall into the one part will fall into the column space of a, and other part of b would be in the left null space of a, that is e part, right? And this b vector will be you can write it as ax hat plus e, right? So this is how you can write. Okay, now if these two are perpendicular, we can say that the a dot e, this will be also orthogonal plane, right? The subspace is spanned by the a or the e, right? These will be orthogonal also, and we can write e as b minus ax. So b minus ax hat is equal to 0 from here. So not now we can take the transpose. Here we are writing the dot product. Now the same thing we can write like this, right, in the matrix form. So from here we will have a transpose b is equals to a transpose a x hat. So from here we can write x hat as a transpose a inverse a transpose b. So this is what we have to find, x hat, right? So to find that, we need to calculate these things, right? Let's do that. So a transpose will be 1 1 1 and 1 to 4, and a is 1 1 1 and 1 to 4. We can do the multiplication, so that will be 3 and 7 and 7 and 16 plus 4 20 plus 1 21. Now we can take the inverse of this matrix, because we have to find the inverse of this a transpose a, right? So here it is, this is a transpose a. Now we can take the inverse of this, so that will be these two rows, these two diagonal element will get extend, and sign of this will get changed. Also we will have the determinant of this, so that is 63 minus 49, that is 14, right? So now we have to do this part also. Let's carry out this. So a transpose is 1 1 1 and 1 2 4, and b is, so b is already given, right, this one. So 604 640 we can calculate, so that will be 10, and this will be 3, no sorry, that will be 10, and this will be 8 plus 6, that is 14, right? Now again you see we will have to carry out this complete multiplication, so that means this matrix or this matrix, we can do that. So that will be 1 by 14, and here we will have 210 minus 98, so that will be, I think, 1112. And here we will have minus 70, and that is 42, right? So that will give you 28, right? And that will be in minus, right? So finally we have got this. This is your x hat, right? So from here we will have this will be 8 and this will be -2. Okay, now we have answered this part, best x hat, and the error e. So error e, how you can find from this equation, right? So that will be uh, x hat we have found, and error will be a is equals to, that will be b minus ax hat, right? B minus ax hat. So that is b minus ax hat. So b is 640, that is given, and ax hat is, you can find it, right? So ax hat a is 111124 and x hat is 8 minus 2. We can carry out this multiplication, that will be 8 minus 2, that is 6, 8 minus 4, that is 4, 8 minus 8, that is 0. So this is what we get, the e. No, this is not the e, but so we will have to subtract this b, right? So 640, b is 640, that will be e. So that is the 0. Okay, now this is something interesting. So the point is that when you projected this vector, so this is what the projection part is, right? So you are getting this part e, that is 0, right? What does it mean? That this was already in the column space of this a, right? Suppose, let me give you an analogous picture. You are at, let's call this line, and this vector b is itself on this line. What will be the projection? The projection will be itself b, right? So this is the projection part, and you see that this part is the same as b, right? And what will be the e of this? That will be the 0, right? The other component will be 0. So I have gone through the general process of finding the best x. So you can apply this process to any problem. If you have similar kind of problem, then you can apply this whole process and you will get the answer. In this case, what happened, that we at the end we found that this b is already in the column space of this a, right? That is why we at the end we found that there would be no error term, or there would be no second component of this b, because that is already in the column space, right? So that is all about this question. Thank you. Okay, so let's look at this question 3. So suppose v is an unit vector. So v is a unit vector in R3. That means b will have the 3 components, right? Since it is in 3 dimension or R3. The question is about the matrix H is equals to this 2 v transpose minus identity matrix. The first part of the question is that multiply H times H to show that H square is equals to I. So let's first solve this part A. So we have to show that H times H is I square, and we have this matrix H, right? So this H is 2 v transpose minus I, and this v matrix is a unit vector in 3 dimensions, so that will have the 3 component. Let's assume that is v1, v2 and v3, right? So if you So now we can multiply h by h, and again same thing here, that is 2v transpose minus I, that is the 1h, and 2v transpose, this is the second h, right? We can do the multiplication, so that will be h square, and this will be 4 v transpose v transpose minus, if we multiply with the identity, then we are going to get the same matrix, that is 2v transpose and minus 2v transpose and plus I square, that is again it is going to be I. Now look at this one, this part. So this is v transpose v, right? So what is v transpose v? So v transpose will be v1 v2 and v3, and this is v, right? So if you will find this v1 v2 v3, that is the v transpose, and this v1 v2 v3, what you will get is the v1 square plus v2 square plus v3 square, and this is nothing but the length of your, or the norm of your vector v, right? And this is 1, because this v is a unit vector, so that means this is 1 length of the vector, and that will be 1. So that can be further simplified as 4v v transpose minus 4v transpose plus I. So from here what you can see, that is equals to I. So h square is equals to identity matrix. So first part is done. Now let's look at the second part. So second part, what it is asking, that so that h passes the test of being symmetric. So h passes okay, so matrix is symmetric if we take the transpose. So we have given this matrix H, that is 2v transpose minus I, right? Now if we take the transpose of this matrix, then we should get the same matrix. That means if we take the H transpose, if we get the same matrix, that means matrix is symmetric. Okay, now let's take the transpose of this. So transpose both side, so that will be okay, so here we can transpose individually, right? So that will be 2v transpose of transpose, that will be transpose, and here we will have v transpose minus transpose of I, you will get the same I, right? And this is the v. Okay, so here we will have no transpose, right? Because v transpose of transpose will be cancel out, so here we will have v transpose, right? That is again what we get is again this part, you see, that is again the H, right? So that means this matrix is symmetric, right? Yes. Now it has one more part, that so that this is a orthogonal matrix. So it is if it is a orthogonal matrix, then we need to have that H transpose H is equals to identity matrix. If this condition is getting satisfied, then we can say that H is a orthogonal matrix, right? And this is the condition for symmetric. So so you see that this H transpose is again H, and this is H, right? In part 1 we proved that H square is nothing but the identity matrix. So we can say that this H is a symmetric and the orthogonal matrix. Now part C, we have to find the eigenvalue of H. Eigenvalues of H. Okay, so H we have given, that is 2 v transpose minus I. Now we have to find the eigenvalue of this H, right? Let's assume that this is some matrix M, right? Then we can write this 2m minus I, where m is equals to v transpose, right? And this v is v1, v2, v3, and this v transpose is v1, v2, v3, right? uh, we can, okay, now if this m has eigenvalue, that is lambda, then what will be the eigenvalue of this H? That will be 2, this is m, right? So 2 lambda minus 1. So the eigenvalue of this H will be 2 lambda minus 1, right? So we have to find the eigenvalues of this H, right? So this, if so, the point is that if we can find this lambda, then we will have the eigenvalue of this H also, right? If we have the eigenvalue of m, then we will have the eigenvalue of H also. And this m is, you see that this one, v1, v2, v3, and v1, v2, v3. So what will be the rank of this matrix M? That will be 1, right? Because if you do the multiply, what you will do, what you are going to get is the v1 square and v1 v2 and v1 v3, right? And again v1 v2 and v2 square and v2 v3 and v1 v3 and v2 v3 and v1 v3 square, right? This is what you will get. So what's the rank of this matrix? So the rank of this matrix is 1. Why? You can directly look at this, that this matrix is nothing, that this column, you see that it has the v1, right? v1, v2, v3, it has the, let me write it down like this, so that you can see why it has the rank 1. So it is v1 and this is v2 and this is v3 into v3, right? So we have this v1, v2, v3 here, and v1, v2, v3, and v1, v2, v3, right? So this is nothing but the linear combination of this, like you can write like v1 into v1, v2, v3 plus v2 into v1, v2, v3 plus v3 into v1, v2, v3, right? So you see that you have one vector, right? And the other vectors are the somehow the scaled version of this. So base point is that it will have the 1 rank, and it has the 3 vector, but the other 2 vectors are the some scaled version or some linear combination of this so it has only one independent vector. So this m will have the rank 1, so rank of this m is 1. So what does it mean? That this is 3 by 3 matrix. That means it is rank 1 matrix, right? So that means we will have the value, that one value that will be non-zero, and other two eigenvalue will be 0, right? Now question is how we can find this lambda 1. So we know the trace of the matrix, right? if we can make use of the trace of the matrix, that is nothing but the sum of the diagonal elements. So that is lambda 1 plus lambda 2 plus lambda 3, and if you find the trace of this, so that is going to be v1 square plus v2 square plus v3 square. And if you see that this is nothing but a unit vector, so that is 1, right? And this lambda 2 is 0, lambda 3 is 0. So from here what you find is lambda 1 is equals to 1. So we have found all the eigenvalues of matrix M, that is 1 comma 0 comma 0, that is lambda 1, lambda 2 and lambda 3. Now if we have the eigenvalue of this matrix M, that is lambda, we can find the eigenvalue of this matrix H. So that will be the eigenvalue of this matrix H will be 2 times lambda 1, that is 2 minus 1, that is 1, 2 minus 2, or that is minus 1, lambda, when lambda is equal to 0, when lambda is equal to again 0, that will be again minus 1. So the eigenvalues of this matrix H will be 1, minus 1 and minus 1. Okay, that solves our question, this part C.